Welcome to homework.
In this problem, we are given the 7 different chemical species, and in part A, we want to determine which one is the strongest oxidizing agent, and in part B, we want to determine which one is the strongest reducing agent. Remember that an oxidizing agent is being reduced, and a reducing agent is being oxidized. And so we can go through and look at each of these 7 reagents that we are given and determine which ones will undergo reduction and which ones will undergo oxidation. Starting with the reductions, we know that Na plus can be reduced to solid sodium by adding an electron. It cannot be oxidized to give us an oxidation state of sodium greater than +1. We can also reduce Ag plus to solid silver by adding an electron, and we can reduce Zn2 plus to solid zinc by adding 2 electrons. So those are the 3 species that can be reduced, so the remaining must be oxidized. We oxidize Cl- to Cl2 gas. We increase its oxidation state by losing electrons. Furthermore, the solid states of any metal correspond to a species that will be oxidized because we have to lose electrons in order to increase the oxidation state of those metals. Metals cannot have an oxidation state less than 0. And so that is why we know that the solid metals will be oxidized. So now we know that the species in red will be reduced, and these correspond to those reduction half reactions for all of those 3 species, Na plus, Ag plus, and Zn2 plus, that can be reduced. And we can look up their standard reduction potentials from the table that provides us with those standard reduction half reactions along with those standard reduction potentials. Furthermore, the species that can be oxidized are in blue, and those correspond to these 4 half reactions, which when we look these up in the table, they are written as reduction reactions. So Cl2 plus 2 electrons to reduce Cl2 to 2Cl-, and so on. But if we reverse these to give us the oxidations of each one of these species, that is Cl-, Ag, Zn, and Pb solid, then the standard reduction potentials, after we reverse their signs, correspond to the standard oxidation potentials. So we can use that information to help us first work through part A, where we want to determine what is the strongest oxidizing agent. An oxidizing agent is being reduced, and these are the species that can be reduced, Na plus, Ag plus, and Zn2 plus, and these are their reduction half reactions with the values of their standard reduction potentials. So we have to compare the relative orders in terms of magnitude for the standard reduction potentials. We see that out of these 3, the largest or most positive is 0.80, corresponding to the reduction of Ag plus to solid silver. And so therefore, since that half reaction has the greatest standard reduction potential, then that means Ag plus has the greatest potential to be reduced. And that would make it the strongest oxidizing agent. So that is why the answer for part A is Ag plus. And now in part B, we want to determine what the strongest reducing agent is. Reducing agents are oxidized, and we know that these are the 4 species that we are provided that undergo oxidation. When we write out the oxidation half reactions for each one of these species by reversing their standard reduction potentials to now correspond to standard oxidation potentials, we again compare them to see which one has the largest oxidation potential. And we see that 0.76 is the most positive value out of these 4, which corresponds to the oxidation of solid zinc to zinc 2 plus. And again, if we were to write these out as they are given in the table as reduction reactions, then if we flip the signs of all these, then that corresponds to the given standard reduction potentials that we are given in the list, in that table. And so if that's the case, then that negative 1.36 would be positive 1.36 as it shows in the table. And that would correspond to the most positive value, but that would be for the reduction of Cl2 to Cl-. So Cl2 being reduced to Cl minus has the strongest potential to be reduced and therefore the smallest potential to be oxidized. So either way you look at it, whether you look at the most negative standard reduction potential or the most positive standard oxidation potential, we can see that solid zinc is the strongest reducing agent. So that is the answer to part B. And now in part C, we want to know which species can be oxidized by SO42-. If we are oxidizing a species by using SO42-, then SO42- must be acting as an oxidizing agent, and therefore SO42- must be being reduced. And so when we look up on the table, this is the half reaction that corresponds to SO42- being reduced by adding electrons. And this is its corresponding standard reduction potential. And we know that in order for a species to be oxidized by an oxidizing agent, that when we go to calculate the cell potential, it has to come out to a positive value. And we know that when we are calculating the cell potential, we take the standard reduction potential and we add it to the reverse of the standard reduction potential for the species undergoing oxidation. So these are, again, the 4 species that undergo oxidation. And we have reversed their standard reduction potentials to now correspond to standard oxidation potentials. So remember that when we go to calculate the overall cell potential, we add the standard reduction potential for the species being reduced, SO42- in this case, we add that to the standard oxidation potential after we reverse the sign to convert these standard reduction half reactions into oxidation half reactions. So we go through and we add, starting with negative 1.36 for the first oxidation. If we add that to 0.20, we see that comes out to a negative value. So Cl- cannot be oxidized by SO42-. Negative 0.80 plus 0.20 still comes out to a negative value. So Ag solid cannot be oxidized by SO42-. The remaining 2, that is solid zinc and solid lead, are added to this positive value of 0.20 for the standard reduction potential of SO42-. So those both come out to positive values for the overall cell potential. And so that means that Zn and lead can both be oxidized by SO42-. And finally, in part D, we want to know which species can be reduced by solid aluminum. So this is similar to part C. Since we are looking for a species that can be reduced by aluminum, that must mean that aluminum is a reducing agent and is therefore undergoing oxidation. When we oxidize solid aluminum, we go from Al as a solid to Al3+, and we lose 3 electrons. And when we write out the half reaction in that way to correspond to the oxidation, we flip the negative 1.66 corresponding to the standard reduction potential to give us a standard oxidation potential of oxidizing aluminum. And so now, this time, we look at the species that are being reduced, and we add those values to the value of 1.66 to get the overall cell potential. And whichever ones are positive will correspond to species that can successfully be reduced from the oxidation of aluminum. So 1.66 plus negative 2.71 gives us a negative value. So Na plus cannot be reduced by aluminum. Positive 1.66 plus 0.80 gives us a positive value, and negative 0.76 plus 1.66 also gives us a positive value. So we can conclude, based on those positive cell potentials, that Ag plus and Zn2 plus can both be reduced by the oxidation of aluminum. So that means the answer to part D is Ag plus as well as Zn2 plus.